Okay. So last time we got up to the fact that vectors are commutative, which means that v plus w is equal to w plus v. The reason that vectors are commutative, well, you can go into the components. So last time we got up to the fact that vectors are commutative, which means that v plus w is equal to w plus v. And the reason for this, well, let's try to go into the components. So let's imagine that v is equal to v1 and v2, and w is equal to w1 and w2. Then v plus w is going to be equal, if we put together the components, to v1 plus w1, v2 plus w2, which is going to be equal to w1 plus v1, w2 plus v2. Right, I just flip these. And then this is equal to w plus v. So that's how we see that vectors are commutative, and that's what the book is doing over here. And then the next part is linear combinations, which is more relevant to linear algebra. So I'm going to skip this. I don't think it's very relevant for multivariable calculus. Okay, and now this is the unit vector. So any vector with length 1 is going to be called the unit vector. And so that means that if the magnitude of your vector is equal to 1, then you're a unit vector. And any unit vector has the form cosine of theta and sine of theta. So why is this? And lies on the unit circle if you put the origin, the tail of the vector at the origin. So why is this? Well, so we know that x is equal to r cosine of theta, and y is equal to r sine of theta when you have some line over here, but you can really think of it as a vector. And yeah, this is the x component, this is the y component. So this over here is the point, or the vector, r cosine of theta for the x component, and r sine of theta for the y component. Now if r is 1, because the length of this thing is 1, r represents the length of the line, then we would have that this is cosine of theta sine of theta. So any vector like this, and over here theta represents the angle that this line makes with the x-axis. So any vector that has unit length can be represented like this. You just use theta to determine how much, what's the angle that that vector makes with, let's say it's a vector like this, what's the angle that that vector makes with the x-axis, and then it has length 1. And in fact, the length of this vector is 1, because that if my vector is cosine of theta, sine of theta, then its magnitude is going to be the square root of cosine of theta squared plus sine of theta squared, and this is going to be the square root of 1, which is going to be 1. So the magnitude is in fact going to be 1. So yeah, that's why any unit vector can be given in this form with the tip, with the tail lying at the origin. And with theta, the angle between the line and the x-axis. Oh yeah. So in general, if you have a vector v, so let's go back here. If you have a vector v, and let's say it's this vector, and you want to find the same vector as the vector v, pointing in the same direction, sorry, but with 1 for the length. So same vector, but the unit vector. Same direction, sorry, but the unit vector. So one way to do it is by looking at the vector, and we're going to call this vector EV, which is going to be equal to V over the magnitude of V. So you basically multiply V by the magnitude of V, or sorry, by 1 over the magnitude of V. And this shrinks your vector down to the length 1. So let's see why that is. If you look at the magnitude of EV, that's going to be, if you look at the magnitude of VV, that's going to be 1 over the magnitude of V times the magnitude of V. So you basically take out this constant from, right, if you remember, the magnitude of lambda V is equal to the absolute value of lambda times the magnitude of V. So this over here is my lambda, and I just took it out of the absolute value over here, and sorry, of the magnitude over here, and so then these cancel, and we are left with 1. So, and this in fact does have the same direction as V. EV has the same direction as V, because that it's just V times a scale, and we know that those have the same direction. It just squeezes or stretches your vector based on what you're multiplying it by. So yeah, so going back here, that this is the proof that we just did to show that the that EV is in fact a unit vector. And so in general, any vector V can be written as the magnitude of V times cosine of theta sine of theta. And this again goes back to this. Every unit vector can be written as cosine of theta sine theta. Cosine represents the x component of that unit vector, and sine represents the y component of that unit vector. And so any vector in general, you can just multiply by V over here. So the magnitude of V in this situation is actually equal to R. So like I said before, we have that x is equal to R cosine of theta, and y is equal to R sine of theta. So in general, if you have the vector V, which let's say is going to be equal to V1, V2, we can imagine that V1 is X and V2 is Y. So this is this will be equal to R cosine of theta, R sine of theta. Now the r is just the magnitude of your vector. So this actually is going to be equal to the magnitude of v cosine of theta, magnitude of v sine theta. And then you can just take the magnitude out. So this will end up being the magnitude of v times cosine of theta, sine of theta. And that's this right over here. So the vector can be written as its magnitude times cosine of theta and sine of theta. Okay, so now they want us to find the unit vector in the direction v, which is 3, 5. So 3, 5, they want us to find the unit vector. So my vector v is the vector 3, 5. So what's its unit vector? So first, the magnitude of v is going to be equal to the square root of 3 squared plus 5 squared, which is going to be equal to the square root of 9 plus 25, which is going to be equal to the square root of 34. So that's what the magnitude is. And now the unit vector EV is equal to v over its magnitude, which is going to be 3, 5 over the square root of 34, which is going to be 3 over the square root of 34 and 5 over the square root of 34. Okay, so yeah, 3 over the square root of 34 and 5 over the square root of 34. So now they're showing us that there is another way to express how to write vectors, and that's with i's and with j's. So in general, if you are in 2 dimensions, you can take the following vectors. You can take I to be equal to the vector 1, 0, and j to be equal to the vector 0, 1. So here on the graph, I is this vector, this is the vector I, and j is this vector. And now any vector can be written as the sum of these two vectors. So if I have a vector v, which is, let's say, equal to ab, then v is also going to be equal to ai plus bj, right? Because this is equal to a 1, 0, which is my I, plus b, and then 0, 1, which is my j. And then this over here is going to be equal to my AB. So if I put my A in here, and if I put my B in here, that's going to give me A0 plus 0B, which is equal to AB. So this is just another way to write what V is. You can think of V as being AI, which is the X direction, so the amount that you have in the X direction, plus BJ, which is the number, the component in the Y direction. Right, so the vector 4 minus 2 can be written as 4i minus 2j, and 5, 7 can be written as 5i minus 7j. Okay. So let's see. So this is a physics problem which has to do with separating the x component and the y component of your forces. I'm not going to focus on this because I'm not sure how much it comes up in multivariable. And this over here is the triangle inequality for vectors. And yeah, so I think I'm going to start from this next class and continue to the summary and continue from there. So this is not going to be very long. Yeah, then next time we'll continue from the triangle inequality. Okay.